All right, moving right along. Last time we talked more about part one of 1.6. The story here is we are working on descriptive statistics, so ways to summarize data. And in part one, those ways will all be numeric measures. And what we learned first is that you can summarize a set of data by talking about the center informally of its data. We learned three different metrics for that: mean, median, and mode. I told you to focus on the top two and maybe some theory about one of them. I don't know if I can make that obvious enough that the median is resistant to outliers. And then the more recent video, the last one, the painfully long one about measures of spread that I probably should have broken up into two videos so it wouldn't be quite as painful. I could have done all of this in a separate video, I bet. Anyways, we talked about measures of spread, specifically range, interquartile range, and standard deviation. And I believe I told you to focus on the latter two here, interquartile range and standard deviation. Know how to get these things out of your calculator and know a little bit of theory about one of those things, namely that the interquartile range is resistant to outliers, much like the median is. What I want to do in this video, which will be the last of the videos in part one of 1.6, is talk about some things you can do with what you've learned so far. All right, so it's kind of applications of this stuff that we've learned. I guess I can write that, sure. Applications of 1.6 part one. And when I say 1.6 part one, I'm talking about descriptive statistics, but numerical measures. So not drawing pictures to summarize all your data, but calculating numbers like the interquartile range, for example, to summarize your data. And we're going to talk about three of them, three different applications. I think increasing order of importance. This first one, not super important, but I want to talk about it very briefly. And then two more that are a little bit more important as the class goes on. The first way you can kind of sort of use the things that you've learned so far is by creating something called a 5-number summary. I don't think there's a hyphen there, maybe here, whatever. A 5-number summary is just like what it sounds like, 5 numbers that serve as a summary of your data. So the idea is you have a data set. It doesn't matter which one we look at here, the one in green, the one in blue. What color is my pen right now? It's blue. Maybe we'll do the one in blue here. Some data that I still have saved in my calculator under list 1. If I hit stat and then edit, you can see it here in list 1. At any rate, I might be interested in summarizing this data, but not just with one single number, but maybe with 5 numbers. Well, you're in luck. There's a thing called a 5-number summary that does exactly that. It gives you 5 numbers, and those numbers often are just written as numbers in an ordered list. So like a number, comma, another number, comma, another number. And they don't write like, this is what the first number means, this is what the second number means. They just give you 5 numbers, and from the context, you, the statistician, are supposed to know what it means. Let me show you what a 5-number summary is. Well, like I said, it's 5 numbers. The first number that you see written, it's just the smallest number in your data set. So in this data set, my smallest number is a 1. My minimum observation is a 1. So the first thing I'd put in my 5-number summary would just be the number 1 and then a comma. I don't say minimum equals 1. I just say 1. The reader recognizes, oh, it's a 5-number summary. That must be the minimum. The remaining 4 numbers are all things you've seen before. If you recognize all of them by their symbols, that's good. Q1, your first quartile, aka your 25th percentile. That's the number that is kind of on the lower end of your data set, the number that separates the bottom 25% from the top 75% informally. That comes straight out of your calculator. Q3, same idea, except that's the third quartile, or the 75th percentile. MED is the symbol we've been using for median. Saw that up here 2 videos ago. And then max, kind of like min, stands for the largest observation, the maximum observation. And the nice thing about a 5-number summary is it's a common enough thing to use to summarize data that your calculator gives it to you pretty directly. So if you hit stat and then go over to calc and get back into this one variable statistics screen that we've used several times. I think I said that I am going to do this list, this blue list, which I have saved in L1 in my calculator. So I'll tell my calculator I want to do one variable statistics on L1. Hit calculate, it'll give me this output, which is hopefully somewhat familiar at this point. Hopefully you can look at X bar and recognize this is my sample average. You could look at S and recognize this is my sample standard deviation. That'd be great. If you scroll down a little bit, the last 5 numbers conveniently are exactly your 5-number summary. So the minimum value is 1, the first quartile is 2, the median is 4, the third quartile is 9, and the maximum value is 23. That's a little better. That's my 5-number summary. I don't have a whole lot to say about a 5-number summary other than it's a thing that exists. Somebody gives you this, you are supposed to know that, it's a 5-number summary. This must be my median right here, even if there's no context, even if it doesn't say MED equals this thing. If I'm being perfectly honest, that's what happens in academia. In a more applied setting, what would probably happen is the reader wouldn't want to trust, or the author wouldn't want to trust that the reader recognizes this as a 5-number summary. So they might actually say the minimum equals 1, the first quartile equals 2, the median equals 4, and so on. But in this idealized academic world, we're going to pretend that if I just give you this and be like, here's a 5-number summary, you know exactly what the third quartile, for example, is. Or if I ask you to make a 5-number summary, without telling you what a 5-number summary is, you know what numbers to come up with. That's all I got on a 5-number summary. It's a thing that exists. Next thing I want to show you is what's called a z-score. This is kind of a weird thing to teach because right now it's like, why would I ever care about that? When I show you what a z-score is, you're going to be like, all right, I guess I'll do that for you. If you really want me to memorize this formula and give you this number, I can do it. But I don't really see the importance of it right now. What you'll see is in the second half of this class, where this class gets significantly more difficult than it is in the first half, these are super important. Understanding what a z-score is really important. What a z-score tells you is how many standard deviations above, or if it's negative, it would be below, the mean an observation is. So to be clear, a z-score is specific to one observation. So I can't just give you a bunch of data like I have in blue here and be like, what's the z-score? Like, what are you talking about? What's the z-score? But I could say, what is the z-score of an observation of 9, for example? Or what is the z-score for an observation of 12? Or whatever I wanted. And all that is figuring out is how many standard deviations. Remember, our standard deviation here was, I don't know if we've even calculated it yet. Maybe we'll calculate that in just a second. How many standard deviations above the mean, which was this 6.07, I know we calculated that, is your observation. So if the mean were 10 and the standard deviation were 5, an observation of 25 would have a z-score of 3. If you followed all those numbers, that's really good. Wait, what just happened there? If the mean were 10 and the standard deviation were 5, an observation of 25 would have a z-score of 3. And that's because 25 is 3 5s above 10. Okay, that's a lot of numbers. Let me write instead of talking. So let's suppose we were asked to find the z-score of the observation, or maybe the senior citizen, who walked 9,000 steps. Maybe I'll say in the first data set. So what I'm saying is if you go up to this first data set right here, one of our observations was 9. One of our observations was a senior citizen who walked 9,000 steps. You might be interested in some reason, which really doesn't make sense now, but will make sense later in the class, what the z-score is of this observation. And well, if you want to figure out the z-score, you're like, the z-score is how many standard deviations above or below the mean the observation is. So I need to know the observation, 9 in this case, the mean, which it's a sample mean, so we use the symbol x bar, and that was given in one variable statistics here. It's the 6.07 if we're rounding to 2 decimal places. And then I need to know the standard deviation. And it's the sample standard deviation, so we might as well get comfortable with the symbols. That's the letter S. If I'm rounding that to 2 decimal places, it would be 5.82. And so you can figure out the z-score by saying how many 5.82s is 9 above 6.07. If you're mathematically inclined, that might bring to mind this formula. Wait, what just happened there? The observation minus the mean tells you how far above the mean this observation is. So 9 minus 6 is about 3. This person walked about 3,000 more steps than average. But that's not what the z-score is asking for. It doesn't want to know how many more steps than average did this person walk. It wants to know how many more standard deviations than average. So I have to divide that by the standard deviation to figure out how many standard deviations there are in that 3. So I come over to my calculator here. My observation, 9, minus 6.07. And then I'll hit enter here because I want to make sure that I divide this entire thing by the standard deviation. Then I'll hit divide and it'll take the most recent answer and divide that by 5.82, my standard deviation. I hit enter, it gives me the z-score. Maybe I'd ask you to round that to 1 decimal place, and so you say 0.5. Note that you really shouldn't round the inputs that go into a formula. That's why I told you to keep 2 decimal places here and only 1 here. Generally speaking, if you round things that go into a formula, it can throw your answer off by more than the tolerance that you're looking for. Not a big deal as far as I'm concerned, but that's the kind of thing that could screw you up in the homework. If it asks you for a z-score, don't round this number. Keep a whole lot of decimal places just to be safe. Same with this number. And then you can get your z-score and round your final answer, not the intermediate steps. At any rate, what this is saying is this senior citizen walked about half of a standard deviation more than average in this data set. And that's what a z-score tells you. It's a normalized value. It gives you a way to compare observations across different sets. But that's all stuff you're going to learn in future videos. For this video, really, I just want you to be able to calculate the z-score for an observation. I want to be able to say, find the z-score for, and then give you one of the observations and have you figure it out. And note that if the observation is bigger than the mean, my numerator here will be a positive number. Because if I have a big number minus a small number, it's a positive number. And since the standard deviation is always positive, a positive divided by a positive will be a positive. However, if the observation were less than the mean, if instead of being a 9 here, this were a 2, 2 minus 6 is negative 4. So this would have ended up being negative. If my observation is less than the mean, I get a negative z-score. All right, do I need to know that? Not really, I guess. I mean, it might help add some intuition. But as far as what I will test you on, I will ask you to calculate the z-score and maybe ask you what it means. And you say, all right, here's the z-score. I calculated it. What's it mean? It means this person is half of a standard deviation above average. That's it. That's z-scores. That's the second of the 3 things that we want to talk about as far as applications go. Tell you the third, and then we'll call it a video. Third one, I kind of like the third one. It's talking about outliers. So it's a topic that we've already introduced in this class, but I haven't defined them for you yet. And an outlier is just an observation that's significantly different than the rest of your observations. So in this instance, when this was 235 or whatever it was, I think you probably agreed that, yeah, that would definitely be an outlier if it was 235. But what if it weren't? What if it were 23? Is 23 significantly different from the rest of these? I'd say yes, but you might argue that it's not. I mean, because it's kind of a subjective definition, right? What do you mean significantly different? I mean, yeah, all of these are, it's almost twice as big as your next largest value. That's pretty big. But I don't know. Okay, so maybe we all agree 23 is, what if it were 18? Would that be one? Some of you are probably like, yep. Some of you might be thinking, no. And most of you are probably thinking, I don't know. Why don't you tell me? All right, I'd be glad to tell you. What I want is a non-subjective and objective criteria for determining outliers. I don't want to have to look at this and be like, is this significantly different from the mean? I want to have a formula that will give me a cutoff. And anything above that cutoff or below that cutoff, if the observation is significantly smaller than the rest of them, is an outlier. Unfortunately, some such things exist. The way you can determine outliers is by building fences. So what I'm going to do is I'm going to give you a formula for something called a lower fence, which typically I will abbreviate as LF. And then I'm going to give you a formula for something that I'm going to abbreviate UF. And you might be able to guess that that's just an upper fence. And these will both be numbers that we will calculate. And anything that is less than our lower fence, we're going to call it an outlier. Or if you want to be a little bit more correct, we're going to think of it as a possible outlier. Anything that's above our upper fence, we're going to call that an outlier. Below the lower fence or above the upper fence is an outlier. We're going to build some fences, and anything that's not in between the fences is an outlier. Okay, how are you going to build those fences? Well, what we want to do to build these fences is use measures that are resistant to outliers, right? That's important because you don't want to determine your outliers based on things that are screwed up by outliers, right? Because then if you had an outlier, it would change the metric you're using to determine if something is an outlier in the first place. That seems like a bad idea. I want to use metrics that are resistant to outliers so I can determine what would be an outlier. So you're like, oh, okay, right, I remember some of this stuff. The median, that was the one that was resistant to outliers. Good job, that's true. Also resistant to outliers is the 25th and the 75th percentile, which we used to come up with the interquartile range. If you want to determine your lower fence, you're going to take your first quartile, and then you're going to subtract something. And that something that you're going to subtract is going to be 1.5 times your interquartile range. The logic here is the first quartile is pretty low in your data, right? It's the point that is so low that only about 25% of observations are less than it. But we wouldn't want the first quartile to be our lower fence because then about 25% of our observations would be outliers. That seems extreme. So what we want is not our first quartile, but a number that's less than our first quartile. How much less than our first quartile? Well, there's nothing sacred about this 1.5 multiplier here, but it's what's used in most textbooks, including yours. So it's what we're going to use in this class. We're going to subtract some amount based on how spread out the data is. And the measure of spread that we're going to use is the interquartile range as opposed to the standard deviation because we want a measure that's resistant to outliers. But instead of just subtracting the interquartile range, which frankly would be fine, we're going to subtract a multiple of the interquartile range, 1.5 times that interquartile range, for no specific reason, just because that's a number that's generally agreed upon in the statistical community. That gives you the lower fence. So in this case, if I went back to stat and calc and one variable statistics, and I did my one variable statistics on L1, the data in blue, I could scroll down to find that the first quartile is 2, and then I could subtract from 2 1.5 times the interquartile range, which is 7. Where'd that 7 come from? Recall that the interquartile range is always Q3 minus Q1. So Q3 minus Q1 gives me 7. Careful here, common mistake. People do 2 minus 1.5 and get that answer, and then multiply that answer by 7. Don't do that. Order of operations is a thing. You have to make sure that you do multiplication and division before you do addition and subtraction. You have to do 1.5 times 7, get that answer, and then do 2 minus that answer. Fortunately, your calculator knows all that. You can just type in 2 minus 1.5 times 7, and your calculator will do this part of it first. 1.5 times 7 is 10.5, and then it'll do 2 minus that 10.5 to get negative 8.5. My lower fence is negative 8.5. Well, negative, that's weird. No, not really. It's just saying that in order to be an outlier on the lower end, you'd have to have an observation less than negative 8.5. Granted, in this example where we're counting steps for senior citizens, such an observation wouldn't make sense. These have to be positive. That's just saying you can't have any outliers on the lower end. No big deal. What about on the upper end, though? Is this an outlier? Well, we can figure it out if we could calculate our upper fence. And conveniently, our upper fence has a formula that's fairly symmetric with our lower fence, because this is something you're going to want to have memorized, right? I'm 100% going to ask you this on a quiz. I'm going to give you a data set and be like, determine if you have any outliers by calculating upper and lower fences. And if you don't have this formula, you won't be able to do it. I'm not going to provide you with this formula because I'm mean like that. No, because this is a good formula for you to know. Formulas that are horrible to memorize, I'll provide you with, but things that are manageable for you to memorize, I'm just going to ask you to memorize it because it's a good one to leave this class with. Similarly, there's a formula for the upper fence. It's pretty similar to this one, except instead of starting with Q1, the point that's pretty far down in your data, so far down that only 25% of observations are less than it, we're going to start with Q3. And instead of subtracting 1.5 times the interquartile range, we don't want to subtract from Q3. Right, Q3 is, I guess we're using the blue data set, somewhere in here. We want to add to Q3. right? Because we want a number that's bigger than Q3 to determine our upper fence, to determine outliers. So we're going to add 1.5 times the interquartile range. So in the specific case, Q3 was 9. Don't believe me. All right. I'll go over to calc and do one variable statistics again. There it is. Q3 was 9. And then I want to add to that 1.5 times the interquartile range. The interquartile range is still 7 because it's still 9 minus 2. 7 times 1.5 is still 10.5. 10.5 plus 9 is 19.5. Don't believe me. All right. 9 plus 1.5 times 7. If you didn't want to put in 7, you could do 9 minus 2. You could do Q3 minus Q1 and have your calculator come up with that. Just be careful if you put in 9 minus 2, make sure you have the parentheses, because otherwise it'll mess up your order of operations. Hit enter, gives you this 19.5. What that's saying is any observation that's bigger than 19.5, we would call an outlier, or technically a possible outlier. So this 23 really was an outlier. 235 would certainly be an outlier. But if this were 18, we would not call it an outlier. That is how you build fences to determine outliers, and it's the third of the 3 applications of the stuff that we've learned in 1.6 part 1. And so it ends 1.6 part 1.